The Wacker oxidation is crucial for converting simple alkenes, olefins, into valuable methyl ketones or aldehydes, making it a cornerstone reaction in industrial chemistry, like making acetaldehyde from ethylene, and fine chemical synthesis, enabling straightforward access to versatile carbonyl compounds for pharmaceuticals, fragrances, and other complex molecules, showcasing the first major industrial use of homogeneous catalysis and organopalladium chemistry. The oxidation of ethylene to acetaldehyde with stoichiometric palladium, salts, was initially observed by Phillips in 1894. Later, Smit and co-workers at Wacker-Tsuji discovered a similar type of transformation in aqueous acidic medium using catalytic palladium chloride under aerobic conditions in the presence of cupric salt. This transformation was named after Farbwerke Hoechst, AG, and Wacker-Tsuji GmbH Company as the Hoechst-Wacker process, or simply the Wacker process, which was arguably the first transition metal-mediated industrial process for the manufacture of acetaldehyde. In the quest for a more general method for oxidation, the first modification was executed in the DMF and water solvent system for the oxidation of higher-order olefins. Later, the method was refined by Tsuji, employing a mixed DMF and water system for the selective oxidation of terminal olefins with multiple functional groups, and demonstrated the synthetic utility of this reaction. Today, this advanced form of Wacker oxidation reaction to generate various carbonyl compounds by using palladium-2 as a catalyst, copper salt as a redox co-catalyst, and oxygen as the reoxidant is well known as Tsuji-Wacker oxidation reaction. Mechanism of Wacker oxidation. There are many published mechanisms for Tsuji-Wacker oxidation, and each step in the mechanism was thoroughly studied and reviewed. The widely accepted general mechanism of Tsuji-Wacker oxidation involves the coordination of palladium, salt with dihapto, olefin followed by subsequent attack of nucleophile based on Markovnikov or anti-Markovnikov addition that causes the formation of two regioisomers of the carbonyl compound. The mechanistic studies show that the formation of the product, whether an aldehyde or a ketone, solely depends on the pathway of the hydroxyl palladation and the stereochemistry of the hydroxylalkane palladium complex formed. In the conventional Wacker oxidation, once the product is formed, palladium-2 gets reduced to palladium-0, and hence the foremost line-up to use oxidant was to convert palladium-0 to palladium-2, which has been fulfilled by different oxidants to make the whole system catalytic. Research and development. Over the years, there have been magnificent advancements on the oxidant side that increased the efficiency of Tsuji-Wacker oxidation. Initially, oxidation of ethylene to acetaldehyde was carried out by stoichiometric palladium, chloride solutions in an acidic medium. Later on, Smit and co-workers introduced cupric chloride to regenerate palladium-2 from palladium-0, making the whole system catalytic with respect to palladium. This process was later used in the large-scale production of acetaldehyde due to the recycling of cuprous chloride into cupric chloride by air. Mechanistically, this industrial reaction of ethylene constituted three individual stoichiometric reactions, which overall constitute the catalytic cycle. Although cupric salts hold good oxidizing properties, the main issues with this catalytic system was formation of chlorinated byproducts. To overcome this problem, stoichiometric cuprous chloride has been introduced under aerobic conditions, which eliminates the chlorinated byproducts. However, this catalytic system was very corrosive and created issues about hazardous waste in case of higher amounts of copper used, decomposition of palladium, or isomerization of olefins that invariably limit the Tsuji-Wacker oxidation. These issues became new challenges for quite some time, to enable this transformation to be more efficient, green, and noble. Apart from oxidants, other investigations have been directed to improve the efficiency by variation in the solvent system. The conventional Wacker reaction was reported in an aqueous acidic medium. Later on, the conversion of 1-dodecene to 2-dodecanone in aqueous DMF was documented. Moreover, others like ionic solvent systems and supercritical CO2 were also utilized in the Wacker process, enabling the transformation to be efficient and green. Continuous improvements and overcoming of many issues have been the subject of substantial research in this area for the last 5 decades. Despite substantial improvements with regard to oxidants and solvents, there have always been issues associated with chemical waste, high cost, and safety concerns. Scientists demonstrated the alcohol-coupled Wacker oxidation that eliminated the use of a metal co-oxidant, but it still needed the coreductant for the transformation. The remarkable achievement in this area was found when molecular oxygen or air was introduced as a sole oxidant in the catalytic system, which suppressed olefin isomerization and showed higher selectivity for terminal olefins. Recently, there have been significant developments in Wacker-type oxidations using palladium or other metals, along with various organic or inorganic oxidants. There are noticeable developments in catalytic reaction conditions, such as variation in the ligands for PD and other metals as catalysts, oxidant modifications, and different solvent systems. The shift from PD to other metals like Fe, Ni, CO, Ru, PT, and the metal-free processes are recent reports. The electrolytic Wacker oxidation using platinum is an interesting development, and the use of iron complexes is the right move toward greener approaches. Conclusion: from the conventional reaction to present-day benign process and the varied applications of Wacker oxidation have been extensively adopted at different stages in a total synthesis of natural products and valuable compounds, which is remarkable. The compatibility is astonishing when this oxidation is used at end stages of a total synthesis on advanced intermediates with several functionalities already in place to complete the target molecule synthesis. Future directions could be to develop more benign processes based on non-toxic and cheaper metals, the use of oxygen as an oxidant, scalability, and applications in complex molecule synthesis.